Now, the last thing that we did in Unit 1 with each of the two types of functions we learned was called modeling, which is using regressions to write functions for these different model types. So that's what we're going to be doing today, but like the calculator skills are really simple, so we're going to do that and a little bit more. When we're modeling an exponential function from data, there's either an easy way or a hard way to make this happen. The easy way is if the problem already gives you the common ratio and the initial value. Because when we're writing equations, we're just writing y or f of x, g of x, whatever, equal to the initial value a multiplied by b raised to the x power. So all we need is to know those two numbers, the a value and the b value. And if the question straight up gives you the common ratio and the initial value, boom, done, plug it in, we're good to go. But most of the problems will give you two input-output pairs or a set of input-output pairs, like a table or a graph, something like that. That's level 2, but that's where technology comes in because we're going to use technology to answer those questions. So let's see an easy example right here. This one is going to be like number 1. It says, immediately after drinking her morning cup of coffee, time equal to 0, Miss Quigley has 150 milligrams of caffeine in her system. 1 hour later, Miss Quigley has 4/5 of the original amount of caffeine still left in her system. Find the values of A and B. Okay, so initial value is pretty obvious. What's the initial value for this problem? 150, because we know at time 0, which is the initial value, there's 150 milligrams of caffeine in my system. Okay, so we know automatically that A is equal to 150. Easy peasy. If we kept reading, it says 1 hour later, so just one more input value later, Miss Quigley has 4/5 of the original amount of caffeine still left in her system. That means that our common ratio is 4/5. We were given the initial value and the base, or the factor, the common ratio. So that's step 1. It said find the values of A and B. Congratulations, we found A and B. Easy peasy. It says then use the given data to write two equations that can be used to find the values for constants A and B in the expression for C of t, the amount of coffee in Miss Quigley's system, t hours after drinking her morning cup of coffee. The reason this sounds so crazy is because this is the wording from one of the FRQs in this class. You will be asked to do exactly this on one of the FRQs. It may not be an exponential function, but that verbiage of use the given data to write two equations that can be used to find the values for the constants A and B, you will see that over and over again. So what we need is we need two data points. The first data point I know we have is the input value of 0 and the output value of 150. That's the first data point I know that I have. Can anybody figure out the next data point? What's the only other information that was given in this problem? 4/5. And when did that happen? 1 hour later, and it should be 4/5 of the original amount. With your calculator, what is 4/5 of 150? 120. So we know because we did 150 times 4/5 to the first power, right? We know we have the 120. Okay, this means we can use those numbers as x's and y's in this equation to find A and B. What it will look like is it will look like this. You will say 150 is equal to A times B raised to the 0 power. I know that we know A and B for this problem, but in general, we're not always going to know A and B, and we're going to have to find it. Do you see how I just plugged the y where the y goes and the x where the x goes? If we were going to do that for the second set of data points, what would the equation look like? 120 equal to A times B to the power 1. This right here is a full point on an FRQ for this class. If you can straight up plug those numbers in where x and where y go, you got a whole point on one of the FRQs. We can do that. I don't know about that. Okay, thank you for your honesty. Okay, but what if this problem, this was like an easy level 1, whatever style problem, because I gave you the A and the B value. But what if I don't give you A and B, And instead, I give you information like this. This is really what the FRQ will probably look like in this class. It says the table above gives the number of fans inside a large sports stadium for 0 through 30 minutes. There are 47 people in the stadium 2 minutes after the doors open. There are 2602 fans inside the stadium 20 minutes after the doors open. The number of fans inside a stadium can be modeled by an exponential function. This is key because in this, obviously we're in the exponential unit, but this type of function is going to change on the FRQ, so you always identify the type of function. Where F represents the number of fans inside the stadium, and T represents minutes after the doors open. Use the given data to write two equations that can be used to find the values for constants A and B in the expression for F of T. Then find the values of A and B. This is what FRQ number 2 will start off looking like. This is points number 1 and points number 2 on FRQ 2. We can handle it. All right, we need to look at the data. Obviously, the data is in the table. It's also in the blurb. And I have two coordinate points. I have the coordinate point 2, 47. And what's the other coordinate point? 20, 2602. Okay, great. Well, just like we did in the problem above when it was easy, and even though we knew the A and B, let's plug it into the formula. I'm plugging into y equal AB to the x, or f of t equal AB to the t. So we would have 47 equal to A times B to the what power? To the x power, but in this case, x is 2. What would the second equation look like? Equal to the 20. You just got a point on an FRQ. Amazing. We're just plugging stuff in. Super easy. We can handle. But at this point, the second question on that FRQ is going to ask you to find the values of A and B. We're not going to do this by hand for any of the function types that we have, because this FRQ is calculator allowed. So what we're going to do is follow the steps right underneath it. You are going to enter your data into list 1 and list 2, so that's the stat edit screen. You are going to, once you've typed it in, go to the calculate menu, but you're going to select option 0. Option 0 is our exponential regression. You make sure that boop, 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 you go down, and on store regression equation, you put y1. And then you press calculate. And it will give you the values of A and B. Does anyone need to see a walkthrough of that live? Or are these pictures enough?
Wait, is this how it goes?
Yes. Wait, just kidding. I think I just lied to you. It should be 2, 0, 47, 2602. So the coordinates go sideways. 2, 0, 27. Yes. So when we get this, and we should get the values of A and B, and they are actually what are showing on this paper because it's straight up an example problem. So we have the value for A. What is our initial value? 30 point. Very good. We round to 4 decimals in my class. And B, what is our B value here? How did I get the Y1? Thank you so much for asking. If we forgot, this is alpha, trace, enter. It's a shortcut menu. So we don't have the R's, and you would eventually in this class, we're going to need to turn them on, but honestly, that's more important next class. So right now, if you remember how to turn on stat diagnostics, that should always be step 1 whenever we're doing stuff on our calculator, but you don't need it for today, if that makes sense. But we should try to start remembering to turn that on every time. What was our B value, by the way? We got distracted. Very good. We round to 4 decimals. It's going to tell you to round to 3 decimals on the instructions, but we're going to round to 4 so that we don't make a rounding error. The reader will stop reading after 3 decimals and truncate it for you. So don't round wrong, round to 4 decimals. Questions, comments, concerns? Anybody need an additional calculator help? We're okay? Fabulous. So We have two skills we worked on this front page. We had the skill of finding A and B, either from an easy question where it's given to you, or a hard question where you have to use a regression to find it. We also worked on plugging in the values, the input-output pair, to A times B to the x power. Can we handle both of those things? Great, let's flip it over. Let's make this a little bit more challenging because calculator skills are easy. We've been doing them. Ow, I just hit my knee on my desk. We've been doing them since like elementary school. Probably not actually. When's the first time y'all had a calculator? Freshman year? 5th grade? Whoa. Last year?
I remember using Desmos in 8th grade.
Okay, Desmos in 8th grade. So you did use a calculator. Desmos is a calculator. But these calculators we got to get used to. All right, so an additional moment for us when we're studying exponential functions, there is a base value that we use a lot. E in mathematics is not a variable. E, it represents a number, kind of like pi. You know how pi is 3.141592653588979 and on and on and on, right? I can go to like 27 digits, flex. Okay, but E is the same kind of idea. It is a value that happened so often that mathematicians got tired of writing out a bunch of decimals for it, and we gave it a value E. On your calculator right now, there are 2 places you can type an E button. Can you find both of them? Where's the first one? Second divide gets you E. Where's another one? LN, yeah. Second natural log. If you press the LN button, which is a natural log button, we'll discuss what that means in a few units, or in a few chapters. But that is the 2 ways you can type an E on your calculator. It is a number. It is called the natural base or the natural number. The mathematician who created it or unified it as the letter E, his name is Euler. So if you're Googling stuff online and you run across something called Euler's number, that's the same thing. And yes, that is pronounced Euler. Weird, I know. Okay, so we're going to see this number E in a lot of examples. Just don't panic. It's a base, it's a constant, but we have our calculator. This problem number 3 says, the number of bacteria in a particular culture can be modeled by the exponential function b to the t equal to 17 times e to the 0.31 t, where t is measured in hours. Okay. Let a times b to the regular t, notice that's not 0.31 t, that's regular t, be an equivalent expression for b of t. We're going to find the value of a and we're going to find the value of b for this problem. Okay, finding the value of a is real easy. Can you tell me what the value of a is? 17, very good. We know it's 17 because it's the number in front of the thing with a power. 17 is in front of E. E has the power. That means 17 is our initial value. The B value, however, we need to do a little bit of work. Thinking about what we just learned in topic 2.4, can I rewrite e to the 0.31 t power so that it just has t as an exponent? Yeah, when we had multiplying in the exponent, what did we do? Separated them by doing what? Power to a power rule. Very good. So this is like saying e to the 0.31 raised to the t power. Now that the t is the only power, like this question is asking for, we can figure out the value of b. This is the value of b. In your calculator, can you tell me the value of b rounded to 4 decimals? $1.3634. Very good. So we took the formula we were given, found the initial value easy, and then used our exponent properties that we practiced in 2.4 to rewrite the base as a particular number for the value of b. Questions, comments, concerns? Is anybody lost on, I know I haven't, I'll show my calculator just in case somebody's lost and not asking for help. Let me pause. Part B here says, find the average rate of change of b of t over the interval from 1 to 7 hours. Ooh, who remembers my average rate of change formula? A rock equal Okay, I hear it. F of x2 minus f of x1 over. Great, but let's use the letters and numbers from this problem. Instead of f, what is the name of this function? B. So we're going to have b of x2. What's the second time value that I care about? Yeah, second time value. 7 minus b of the first time value I care about, which is 1, divided by 7 minus 1. It is the average rate of change formula, f of x2 minus f of x1 over x2 minus x1, but changed for our letters. That's b of t2 minus b of t1 over t2 minus t1. Okay, we've got a little bit of work to do. b of 7 is telling me to do what with the number 7? Plug it in. So if I was showing my work, here's what it would look like. I would have the entire function 17 times e to the 0.31 multiplied by 7. Then I'm going to subtract b of 1, which means take the entire b of t function, but plug in the number 1. All of that over 7 minus 1. Thank goodness this is a calculator question, am I right? We're going to type all of that in at one time because we're not going to round and make a mistake on rounding. So we make the fancy fraction. We do 17 e to the 0.31 times 7 minus. I heard, hold on.
Okay.
We're good?
No, I just deleted it.
Oh no, Paula. This is 17 and then e to the 0.31 this time times the number 1. Go to the denominator, do 7 minus 1. Whoa, how are we doing on typing?
Minus.
Don't press delete this time. All right, so once we get that out of our calculator, our average rate of change, if we round to 4 decimals, is 20.9521. And since this is, oh, you can't see what I'm writing because I left my calculator on the screen. Move. Okay, 20.9521. And since normally it's just going to ask you for the number, but this is contextual, so we want to add like what we're talking about. This is measuring the number of bacteria that are growing per hour. Where? Bacteria per hour.
I'm trying to say her slash looked at a negative thing.
Are you saying my handwriting is bad? Them fighting words, man. No, just kidding. I'm just kidding. Okay, letter C says, find the value of T when the number of bacteria in the particular culture is 1,000. So did they give me T or did they give me B of T? They gave me B of T. So they're telling me that the B of T is equal to 1,000. Okay. If I were to try to solve this by hand, we don't actually have the skills yet to solve this by hand because, don't write this down, but our formula would look like this. 1,000 equal to 17 times e to the 0.031, not t, 1t. We don't have the skills yet, unless you remember things from logarithms in Algebra 2, to solve this by hand. And in fact, because this is still looking like the FRQ number 2, which is a calculator-enabled FRQ, we're not going to do this. Instead, we're going to use our calculator to help us. In Y1, we're going to type 17e to the 0.31x. I know that our formula uses t, but your calculator only has x, so we're using the x. And in Y2, we're going to put 1,000. Our goal is to figure out what will happen to these two functions when they meet, because we'll have some sort of exponential and we'll have some sort of constant function. I want this point where they intersect. That's going to give us our answer. Yes? Okay. But this is going to be a little bit of a challenge, and I don't want to tell you how to do this yet, because if you just straight up type this in and press graph, it's not going to work, and I'm not going to tell you how to fix it. I want to see if you can. You ready? Let's try it. Okay, so I'm liking the problem solving I'm seeing. So when we press graph, we see just one part of the exponential, but we don't see where they intersect. Instead of pressing zoom, we go to the window. Obviously, our y value needs to be bigger than what number? 1,000. I'm going to make mine 1,500 because it's kind of, you could do 2,000 if you want it. I'm going to press graph. Here's the exponential. There's the constant. Do I see them crossing? No, it's like off screen to the right. What value do I change on the window to see more to the right? X max, what should we make that? I heard 100. Sure, let's try it. Do I see them cross?
Yes.
Okay. How do we figure out that point of intersection?
Grab. Or, wait,
You
trace.
just move your little
I
mouse.
don't know why.
Even better than that, we're going to make the calculator work harder than us. We're going to press second, trace.
That's what I meant, yeah.
Option number 5 will identify the intersect for you. We press enter, enter, enter. Because we want to be more detailed than just like moving our cursor over, we have to have the decimals right. So we don't want to use just like scooting over. I like that idea, but these are going to be decimals. So we got to be more accurate. Meaning I see that these intersect at the coordinate point 13.1437, comma 1000.
Wait, mine doesn't say that.
Uh-oh.
Yeah.
Did I type something wrong?
I have what you have.
Uh-oh, let's problem solve.
This first curve, question mark.
Press enter. Now it's going to say second curve, right? Press enter. It's going to say guess. We don't guess. Press enter.
Oh.
There we go. Okay. Fabulous. So let's answer the actual question here. If we know that the intersection point between our line describing the bacterial growth and the line 1000 is this coordinate point, what time does the bacteria reach that? 13.1437. I think I just kind of stopped talking in the middle of a sentence there. So sorry.
What time?
What time? I just didn't finish that sentence. I don't know what happened. Okay, so beyond just finding the values of A and B, using our calculator or doing stuff from 2.4 to modify the base or change the base, we always have to be ready for an average rate of change. You're going to see those questions from me and from the test writers. You do also need to use your calculator to solve questions like this. If they give you an output, set the equations equal to each other and solve, meaning we're doing this on our calculator. Can we try one more example? We're doing it anyways. Great. It says after 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equal to a times b to the t, where t represents the number of years since deer were first introduced into the wooded area. I bolded that on purpose. It'll come back later. The population of deer increases by 13% each year. We're step 1. We're going to find the values of A and B and use the values to write an expression for d of t. Let's start with the easy one. What's the initial value? 50. There were 50 deer introduced at time 0. So we know A is equal to 50. Did it give us any information about the base or the rate? 13%. Now, what does that mean? That's a great question. We are increasing by 13% each year. Bless you. What does it mean? What kind of number do I use to show an increase of 13% each year? When we're doing percentage increases or decreases, it's always 1 plus for increase or 1 minus for decrease. That value, 13% as a decimal. So to show a 13% increase, the number I'm going to use for B, 1.13. That's a 13% increase. If it had said 13% decrease, it would be 1 minus 0.13 or 0.87. Okay, now we can use these values to write an expression for D. Our expression for D would be D of T equal to A, 50, multiplied by B, 1.13, raised to the T power. Fabulous. A kind of question you can have when I give you the model here, it says according to the model is this, we just wrote it. This is a model. What is the population of deer in the large wooded area after 6 years? Did they give you an input value or an output value? 6 years, is that T or D of T? T. And it is in years, so that's good. That means that T is equal to what? 6. So I'm really just doing D of 6. There's no fancy anything we have to do for this kind of question, because if we have a value to plug into a model or into an equation, that's all we have to do. So in your calculator, what is 50 times 1.13 raised to the 6th power? I highly recommend using the parentheses that I write on the board in your calculator when you're doing this. 104.76. Okay, cool. If I was writing this on an FRQ, I would probably leave all those decimals there, but since this is actually representing deer, can you have 0.0976 of a deer? No, so it's 104 deer. You'll make it possible. Mad scientists laugh. Mwahaha. Part C is going to be for you to solve. It says, find the time when the population of deer in the wooded area is expected to reach 5,000. This is eerily similar to part C in the problem above. But I want you to do it. I'm going to pause and let you work. Okay, did we find, say again?
Little Mermaid just passed.
Yeah. Did we find the intersection point? Almost. I hear, yeah, you had to really zoom out pretty far to see it, right? But when you get that intersection point, it should be 37.6801 comma 5,000. Yes?
How do I move more this way?
If you need to move more that way, that's your X minimum.
Why is it doing that?
So that make that number 50, Paula.
Oh my god, I'm so off. Okay.
Is that seeing it now?
I'm really doing this.
Okay. So that means that the time when the population of deer in the wooded area is expected to increase would be after 37.6801 years. Because we're measuring in years. Now this next question is really interesting. This is like a push question. It says, find an equivalent expression. That's key that we're using the things from last class from 2.4. Find an equivalent expression for D of t where t is measured in months instead of years. So our problem right here, our t value is measured in years. So just as a bonus, 1 year is how many months? Okay, 12 months. So if I wanted to rewrite this, so I was talking about 1 month, what would I do to the years to get 1 month to represent a year? So we would actually write this as 1/12 of a year. We want our exponent to be measured no longer in years, which is what t represents originally, but in months. So what I can do is I can take this d of t function, and I can say 50 times 1.13 to the, instead of t, because I'm trying to make it a month, 1/12 of t, because it's 1/12 of the original t value. That will be months. But of course, now I see that we have a power raised to a power, so we multiply. Using our skills from last class, we can take that and write it as 1.13 raised to the 1/12 power, all of that raised to the t power. And then I can ask my calculator, because I'm not doing that in my head, 1.13 raised to the 1/12 power.
You got that.
No, you got that.
You got it. Use your thinker.
So we would go to our calculator, and we would do 1.13 raised to the 1/12 power. And our new value for our base, with our change of base, notice the initial value did not change, is 1.0102 raised to the t power. That's our new function in terms of months instead of in terms of years. Oh, you can't see what I'm writing. LOL. So there is going to be a possibility that you will take an already written equation and change what the variable is representing using this idea of a horizontal dilation. So you just have to figure out how to make 1 month in terms of year. And 1 month is a 12th of the year.